Let's talk again about Gaussian elimination. So I'm pretty sure you learned that last year, but I would like us to start on uh, uh, some very deep basis so that we agree what we want to do when we're doing Gaussian elimination. So just to remind you, the idea is that you start with the matrix A. That's, well, let's assume it's invertible, and you write the matrix identity on one side, and you're going to do some transformation on the matrix A. You do them at the same times on the matrix I, so that you transform A into I, and that transforms I into A minus 1. So I remind you, A minus 1 is going to be the inverse of the matrix A. It's supposed to be the matrix such that if you multiply A by A minus 1, whether it is on the right or on the left, that should be equal to identity. If you have a square matrix, you have, well, left inverse and right inverse are the same, so you just need to check one of the equalities. All right, so that's definition of the inverse matrix. So what do we use that for? Many things. And for instance, that could be used to solve ax is equal to b, but I will get back to this idea. If you know a minus 1, you just have to write a is equal to a minus 1 times b. Okay, that seems pretty clear. All right, but there may be some ways to just stop before, not go the whole way until the a minus 1. So that's what it's doing. How is that doing it? That transformation from a to I, okay, so on that side, sorry, on that side, is done into two steps, basically. The first step is to transform A into some matrix that is going to have some zeros below the diagonal, okay? That's going to be what we can call U, as the matrix U as upper triangular matrix. And then from this upper triangular matrix, we're doing some more transformations into transforming that as the identity. Okay, so zeros everywhere except on the diagonal, right? So there are some terms here. The row echelon form. Okay, so this is a vocabulary word that I want you to know. When we say we want to make A as a row echelon form, this is what we are aiming for. Okay, so now let's see what transformations we have to do in order to make A into an upper triangular matrix. Okay, so row echelon form is to make it upper triangular. But you've got many ways to do that, okay? And I want us to agree on the correct way to do that so that you can apply systematically that method without trying to be smart, and it's going to work. Okay, so maybe there are some smart stuff to do, but I don't want I don't want you to apply the smart stuffs. I want you to apply the algorithm so that we know that we are doing it right, and furthermore, it's going to bring us some more information. Okay, so upper triangular matrix. So elimination. Okay. Maybe we can take an example to work on an example. Okay, so let's perform the first step of the Gaussian elimination the way I want you to do it. Okay, so let's take one example. Let's put some matrix. Let's define 2, 4, 6 as the first row, 4, 2, 1 as the second row, and 1, 3, 3 as the third row. Okay, so that's row 1, row 2, and row 3. So you remember, the first thing that you should always remember is that you choose your pivot, so it's going to be that one, and you're going to use that line here, and you're going to combine this line with the second row, and also then you're going to combine this first row with the second row with the third row in order to put some zeros below it, below the pivot. Okay, I don't want to see anyone combining row 2 with row 3 at that step. That has no meaning, and this is the first case of mistakes. Okay, so once you have chosen the row you're going to combine, this is your pivot. This is the row that you're going to use to make linear combinations with in order to put the zeros below it. Okay, so next step. Um, so what do we have? First, we have this row is of course not going to change because that's the pivot row. And then I want you to combine row 2 with row 1 in order to get your expected 0. Okay, so thing is that you've got several ways to do that. You could do 1/2 of row 2 minus row 1, or you could do row 2 minus 2 row 1. I want you to perform these linear combinations, and I will show you why it can be very useful, where the root 2 is the one that gets no multiplication, no scalar multiplication. So that would give you root 2 minus 2 times row 1. Okay, so 0 for the first one, then you get 2 minus 2 times 4, that's -8, that's -6, and then you've got 1 minus 12, so that's -11. Okay, and similarly, I want you for the next step, so to use row 3 minus something times row 1. Don't multiply row 3 by anything. I want it to be like this. Okay, I will show you why this is important. So your row 3 minus, well, obviously row 1 over 2. 1 over 2 times row 1. Okay, because that's 1 minus 2 over 2, so 2 minus 1, so that I get my 0. So 3 minus 4 over 2, that's 3 minus 2, that's 1. And I've got 3 minus 6 over 2, that's 3, so that's 0 here. Good. Right, so let's perform the next step. Next step, I'm choosing my second pivot, which obviously is going to be that one. So that's always going to be this choice of pivot, unless you've got a 0, in which case, at that point, in which case you would need to exchange rows in order to get a non-zero pivot, okay? But I want us to perform first something where you don't have any permutation of rows to do, okay? So now, row 1 is just going to remain the same. Row 2 is going to remain the same because this is my pivot row, and you are going to combine that row 2 with this one in order to put a 0 here. Okay, so same strategy. So row 1 and row 2 remain the same. And so we get sorry about this. So we have 2, 4, 6 for the first row, 0, -6, -11. And in order to put a 0 instead of a 1 here, I need to do row 3 minus, well, plus 1 over 6 times row 2. Okay, so that I get 1 plus 1 over 6 of -6, so that's -1, right? So that's, and then I get 0 minus 11 over 6. So that's just -11 over 6. Okay. All right, so this is my U matrix, my upper triangular matrix. So I have obtained my upper triangular matrix U. One thing that I would like us to see is that if you multiply the coefficients on the diagonal of U, what do you get? If or more precisely, well, multiply the coefficients on the diagonal. Well, we get in that case 2 times -6 times -11 over 6. That's going to be 22. Okay. If you wanted to perform the determinant of this matrix, you would do exactly that. Okay, the determinant of a triangular matrix is going to be the product of the elements of the diagonal. Why? Because if you use the usual way to perform to calculate the determinant, you are going to take plus. I'm going to expand according to the first column, obviously. So that's going to be plus the determinant of that remaining matrix, and the determinant of that remaining matrix is just -6 times -11 over 6. So that's 2 times this one, all right? And that's all. Okay, so the determinant of a triangular matrix is just the product of those coefficients, of the diagonal coefficients. And if you compute the determinant of this matrix, you will see that you also get 22. That's 2 times plus 2 times 2 times 3 minus 3. So 2 times 6 minus 3, that's 6. Then I get minus 4 times, I'm expanding according to the first column, minus 4 times 4 times 3, minus 6 times 3, so that's 12 minus 18, so that's negative 6 times negative 4, that's plus 24. So I'm at plus 6 plus 24, that's 30. And then last one, plus 1 times 4 minus 12, so negative 8, so that's 30 minus 8, that's 22 also. Okay, so the good thing is that we've got 22. That's not a coincidence, and we will show why this has to be true. But this is going to be true only if you performed the elimination the same way I did it, meaning keeping your rows, the row where you're doing the elimination, with a 1 coefficient, okay? Like here, 1 times row 3 plus 1 over 6 row 2. Otherwise, you would have different coefficients and it wouldn't work, okay? So why is that working? And this is very important. So let's call this matrix A. I guess you saw that last year in an exercise. What you can represent the transformation from matrix A to that second matrix that we obtained here by using a matrix multiplication. And more precisely, let us write the matrix that I need to perform that operation, the one where I put the 0 in the first line of row 2, in the first column of row 2. Okay, let's call that I used my pivot 1 and I changed on the second row. Okay, my pivot was on the first line and I changed it on the second row. So what happened? What is this matrix? Well, obviously the first line is going to remain the same, so I get a 1 here. Then the second row of this matrix, what do you get? You performed 1 times the second row minus 2 times the first row. So this is how you do it, okay? Think about that, right? So think about this, and then, well, let's just do one operation at a time. That would just be that first operation, and then I would leave the next row alone. Okay, so let's check that it's working. 2, 4, 6, minus 4, 2, so plus 4, 2, 1, 1, 3, 3. Okay, so you see that everything, this one times that, this one times this one times this is just going to give you the first row of the result matrix. So that's just 2, 4, 6. Then when I'm doing that second row times my matrix, so this is going to be minus 2, the first coefficient, plus 1 times this one, minus 2 this, plus 1 times this, minus 2 this, plus 1 times that. So exactly what we obtained. So that's negative 2 times 2, so that's going to be the 0. Negative 4, negative 8 plus 2, that's just going to be negative 6. And finally, negative 12 plus 1, that's going to be negative 11, right? And the last one, we don't change. Okay, the last row calculation, it's just 1 times the last coefficient. Okay, the other ones gets just 0. So sorry, so it doesn't change the 1, 3, 3. Okay, so similarly, when I want to do then the other operation, this operation, I get so let's give it a similar name. So I'm using line pivot, I'm using my pivot on row 1 in order to take out, to put my 0 here. And so what would be this matrix? This matrix would simply be given by, well, my first row is going to remain, my second row is not changing, and now my third row, we said, was row 3 minus 1 over 2 row 1, so I get minus 1 over 2 row 1, 0 for nothing on the row 2, and 1 times the other one. So what happened? And then, okay, we have one more to write. When I'm doing that last one, so let's give that a name. So that name is, I'm using my pivot on row 2 in order to put a 0 on row 3. So let's call that E23. And that's just, so the first 2 rows are remaining the same, and the second and the last line is taking 1 over 6 for this one and 1 here. Okay, so what do we have? What's the relation? I've got that my matrix U is actually, my upper triangular matrix is actually the result of A that I have multiplied first by E12, then by E13, and finally by E23. Okay, so I've got those 3 matrices that are performing my elimination. That's where the E letter comes from. Okay, these are elimination matrices. Okay, and so if you and that works every time. You don't need to exchange rows in order to perform the elimination. You will always get this kind of elimination matrices. And what can you see on these elimination matrices? They all have ones on the diagonal. Okay, they all have ones on the diagonal. Why do they all have ones on the diagonal? Because I insisted that when you do the elimination, you don't when you perform the elimination, you don't change the coefficient in front of the row you're working on. Okay, so that is going to give you always ones on the diagonal, because this one doesn't change. What changes is the coefficient you apply to the other lines. Okay, so 1 over 2 in that case, we had 1 over 6 in the E23 here, and so on. And the thing is that, again, these are our lower triangular matrices. Good thing is that these are lower triangular matrices, and very similarly, you can compute the determinant. The determinant of all these elimination matrices, if you have computed them this way, it's just going to be 1, because it's, again, you can compute that, it's just the product of the diagonal elements, all right? And if you remember, so about that determinant thing, you know that the determinant of a product is the product of the determinants, so that you get that the determinant of U is going to be equal to the determinant of each of those, the product of all these determinants, and all the elimination matrices have a determinant of 1. So finally, this is equal to the determinant of A. Determinant of A. So that's one very good reasons why we want to perform elimination this way. Okay. Then what's interesting is that, okay, so let's give a name to, let's call capital E the product of my 3 matrices. So let's say that E is the product of all the elimination matrices. So indeed, if you have a 4-4 matrix, you're going to get more E's than that. We're going to get 4 E's, all right? So a 3-3 matrix, you get 4 elimination matrices, okay, to use. All right, so I've got something like Q is equal to E times A, and so that what I want to write now is I want to get a decomposition of A as some matrix L times U. Thing is that the matrix L that I would get from this would be the E minus 1. So let's have a look at what this E minus 1 is going to be, right? So let's take, for instance, this E13 that consisted of keeping first row intact, second row intact, and for the third row, I subtracted 1/2 of row 1. So what would be the contrary of subtracting 1/2 of row 1? Well, it would just be adding 1/2 of row 1. So let's give it a try. Let's give it a try. So I keep the first two rows intact. And instead of subtracting, I'm adding 1/2 of row 1. Okay, 0, 1. What's happening now? If I multiply those two matrices, I get first row 1 times 1, okay, and then 0, 0, and then I get 0, 1, 0. That's just the beginning of the identity. And then I get negative 1/2 times 1 plus 1/2. That makes us 0. Then 0, 0, 0, okay, then 0, 0, 1. Okay, so indeed, that's it. That's exactly my E13 minus 1. Okay, that's as simple as that. So all of these, the nice thing is that all of these elimination matrices are still going to be lower triangulars. Well, they were all lower triangular matrices, and their inverse is also going to be a lower triangular matrix. Their inverse is also lower triangular. Okay, so what does that mean? It means that the E minus 1, which is actually the inverse of E23 times E13 times E12. First, what is the inverse of a product? Okay, if I've got A times B, which are both invertible matrices, that's just going to be, well, what should it be? Well, let's try to, that's just going to be, well, B minus 1 times A minus 1. Why? Because if you've got AB and you multiply this by B minus 1 times A minus 1, you get identity from this, and then you get identity from that. Okay, so you need to reverse the process. A very cute analogy that I heard in Gilbert Strong's lesson was that if you want to put your socks, your shoes on, you first put your socks on and then your shoes. And then now if you want to go barefoot, you first have to take off your shoes and then take off your socks. Okay, so that's it. When you want to reverse the process, you have to reverse the order of the things that you did. All right, so that's just going to be indeed. So that's going to be E12 minus 1 times E13 minus 1 times E23 minus 1. And the good thing is that when you are taking the product of two triangular, lower triangular matrices, you're going to get triangular matrices. Lower triangular matrices. Okay, so well, I let you check that very easily. You can check that visually. So that's going to be a lower triangular matrix. Okay, so that I've got some very famous decomposition. We have decomposed A as L times U, where L is a lower triangular matrix and U is an upper triangular matrix. Okay, and sorry, let me go back. Looking like that. Okay, so well, they should have the same size, and one is upper triangular, the U one, and the L is lower triangular. Okay, um, what is the idea behind that? Why is that very popular? Because if you have decomposed your matrix as LU and you're looking for, let's say you've got three items, x1, x2, x3, and you want to solve A times x1, x2, x3 is equal to B1, B2, B3. Okay, and you know that you can decompose your matrix A as LU. That means that first write that ux is equal to y. So what you want, the first thing you want to solve is ly is equal to b1, b2, b3. Okay, so what does that mean? I'm not talking about inverting completely the matrix, all right? That would be something we can do. You can compute the inverse by doing the complete Gauss-Jordan elimination process. But here I'm just talking about solving for one specific right-hand side, not doing the whole inverse stuff, all right? So if I put ux is equal to y, then I'm solving L times y is equal to something. What does that mean? It means that I've got my lower triangular matrix, okay, times y1, y2, y3 is equal to b1, b2, b3. And this is just very simple to solve because the lower triangular matrix is you've got L11, L21, L22, L31, L32, L33, and then the rest is zeros, y1, y2, y3, and that's b1, b2, b3, and it's very, very simple to solve now, okay? Why? Because you just have to say, well, L1 times y1 is equal to b1, so you find y1. Then you've got L21 times y1, but you found y1, plus L22 times y2 is equal to b2, so you can solve this one. Each time you just cascade down and you find first y1, then you find y2, and then you find y3 with very simple operations. Once you have found your y's, you just write that what's remaining is that ux is equal to y1, y2, y3, and similarly ux is going to be solved because U is an upper triangular matrix, okay? So you begin from the bottom, but you cascade up to find the original solution. Okay, so you first get y3 from the last row, then from the value for you first get x3 from the last row. From the value of x3, you can deduce the value of x2, and from those two values, you deduce the value of x1, and there you go. This is actually one way to solve these kind of linear equations. Ax is equal to b. Okay, using the LU decomposition, which is very commonly which is a numerical technique that is very commonly used. Okay, so very good. Let me just add that this works when your matrix is invertible and that you didn't need any permutation of the rows in order to make that. But if you have permutations, you have permutations, and you should take them into account first. That's it. And you just have to multiply by a permutation matrix. But maybe let's not go into those details yet. Good.